So now I want to present the main properties of Lebesgue integral, namely how it behaves with respect to pointwise convergence. That was what I already said, that we need a good control over the integral with respect to pointwise convergence, and there are the two main theorems, which maybe, I mean, if you forget everything about integration, how the Lebesgue integral is defined and all the nice body, essentially what you really should not forget are those two theorems, the monotone convergence theorem and the dominated convergence theorem, because that's what you usually need in applications if you really want to calculate integrals of complicated functions, or maybe in most of the theory that's also the basic stuff. Okay, so there are two basic theorems which tell you that in very general situations the integral of a limit is the limit of an integral, and the limit is here pointwise, so very weak kind of convergence. And I told you that the integral is first defined for positive functions, because then we can also include infinity as a possible value, and then we go over to general functions where we have to make sure that things are not infinity. And accordingly, there are those two theorems. I mean, they are dealing, one of them deals with real valued functions which are positive, and then we can also include positivity, and actually the conditions which we need there are quite weak. And the other one, the dominated convergence theorem, is somehow for more general functions, for complex valued functions, but we need some stronger conditions to ensure that we don't get infinity. Okay, so the first one is the monotone convergence theorem, which is also often called theorem of Beppo-Levi. And yeah, so what is the frame? So we consider a sequence of functions, fn, but in this case we want to consider real valued ones, so it should be real valued, and of course all functions should be measurable in order to be integrable. So we consider such functions. They should be positive, and the monotone refers to the fact that we assume they are pointwise increasing. So it's a monotone sequence of functions. So we have 0 less or equal f1 of t less or equal f2 of t, and so on. This is for all t. And then, of course, so for each t, this is an increasing sequence of functions. So this has a limit, but the limit might be infinity. But in this frame, infinity is not a problem, so we allow this. So we also consider functions which at some points might take on the value infinity. So this limit we denote by f. So f of t is the limit, so for each t, of fn of t if n goes to infinity, and this is a value, of course a positive one, but infinity might be included. Yeah, and then the statement is very easy. Then the limit and the integration commute. So then we have what we would expect, or what we would hope for, that namely the integral over f of t over the limit, this is actually the limit of the integrals, the limit n going to infinity of the integral of fn of t dh of t. And our integration here, of course, is as before with respect to this distribution function. So in principle, this is for arbitrary measures on R. And here we allow infinity. So it might be that those integrals here converge to infinity, but then really this integral on this side is also infinity. So infinity equal to infinity is also a possibility which shows up. But it also includes, of course, if this limit here is not infinity, then this side is also not infinity. Yeah, so let me note this here. So with possibly infinity is equal to infinity. So in the frame of positive valued functions, the integral can take on the value infinity, and this is well defined and consistent. Good, so that's the monotone convergence theorem. And then maybe the most fundamental one is actually the one where we don't restrict to positive or monotone functions, but just general functions. And then we ask the question, is the integral of the limit of the integrals? And of course, in this generality, it's not true. One needs a condition, but this condition is somehow quite weak, and it's often satisfied and usually quite easy to check. So this is the dominated convergence theorem. Which is attributed to Lebesgue. And there we consider just a sequence of measurable functions. Again, and then of course we assume they converge pointwise. Here, because of the monotonicity, the limit, we could infer that the limit exists, but now we are in a setting we don't have any properties of our functions, so we have to assume that they converge pointwise. So let Fn, indexed by natural numbers, be a sequence of measurable functions for which we assume that the pointwise limit exists. So which converge pointwise. Good. Okay, so let us give a name to this pointwise limit. Of course, we call it f of t. So f of t is the limit n going to infinity fn of t. And now we should talk about the integrals. And of course, a priori, neither the integral over the fn nor over the f must exist in the sense of being integrable, which means that the integral over the absolute value is finite. But now we put a condition which actually ensures that all those guys exist, and also that the limit and the integral commute. So our assumption is actually this assumption, which is in the title, namely dominated, so that we have a dominating function which dominates them all and which is integrable. Okay, so we assume that there exists a function g. This should be in L1 of R with respect to our measure or distribution function. So this is an integrable function, and this dominates them all. So such that the g dominates all the fn's, and then of course it also dominates the limit. So our assumption here, that's a crucial assumption, the absolute value of fn of t is less than g of t for all n in n. Okay, and of course here I assume that g is a positive function. Of course I could also put the absolute value here. Maybe I should do this. Let me do it like this. Okay, so I have a function which dominates all the fn's and which is integrable, and this implies that also those guys are integrable, because now essentially the integral over this is less than the integral over this, but this here is finite by assumption. And then of course the assumption is that the statement is then first of all also the integral over the limit function f exists, because the limit function also has this domination by the g, so the integral exists, but the point is the integral over the limit function is really the limit of the integrals over the fn. So here is the statement. So f is integrable. F is in L1 of R with respect to dh, and we have what we really want, that the integral of f of t dh of t is the limit of the integral over the fn's. So the limit n going to infinity of the integral fn of t dh of t. Good. Okay, and so this is, let's say, maybe the most powerful theorem in integration theorem, and this taking this for itself, this justifies more or less that Lebesgue theory is really a very good and probably the right theory which we want to have for integration. So I mean in integration theory, of course, the very best would be to be able to integrate all functions, and that for all pointwise limits, the limit and the integral commute. I mean, this is too much. That's not possible. So Lebesgue theory does somehow the best thing you can hope for, namely that you can integrate a very big class of functions, measurable functions, and then, of course, okay, you need this integrability. But then, for the pointwise limit, you still, I mean, in this general frame, there are situations where the integral and the limit don't commute, because things might go to infinity at places, and that's hard to control. So what you need is a function g, which is above all of them, and which controls that things are not going too badly to infinity. Okay, but if you have this, and this is a quite weak condition, and it is usually satisfied in many cases. So this theorem is really, it's very useful and can be applied. Is applied at many places, both for calculating concretely integrals, but also for doing a lot of theoretical investigations.